Hi everyone, welcome to today's class. This is my topic number 10, and for topic number 10 I have chosen one topic from chemical thermodynamics, and this is my second lecture of chemical thermodynamics, and the topic is heat capacity and equation for work. Previously I have uploaded one video about the basics of thermodynamics and also the important rules and zeroth law of thermodynamics and first law of thermodynamics. So these are very important to understand overall chemical thermodynamics and solve the question for CSIR-NET. So please watch that video first and then come to this video, because that will be helpful to understand today's topics. Okay, so let's start then. So you all know that chemical thermodynamics is a very important chapter for CSIR-NET chemical sciences. So we should not avoid this chapter, and we should have a clear knowledge and about the basic parts, and also the equations. Various equations are actually important, and the most important is the equation for works for the various kind of systems. Okay, so let's start then. First, I will be talking about heat capacity. So what is actually heat capacity? So let's see. So the amount of heat required to raise the temperature of 1 gram of substance by 1 K or 1 degree Celsius. Okay. So it is expressed generally as this way, and if the amount of the weight of substance is given also, then we can add m here. Okay, so heat capacity will be the amount of heat required for 1 gram. So here mass in gram only. Okay, for 1 gram of substance, and to raise the temperature by 1 degree or 1 K. Okay, so if we write 1 degree here, then we have to put this value as degree, and if we write here K, then obviously K will be, or Kelvin will be, the unit of temperature. Okay, so these are simple things. Now coming to the why two arrows are there. Two arrows are there because two types of heat capacity. Uh, Actually, heat capacity can be expressed within by two ways. Okay, so one is heat capacity at constant pressure, and another one is heat capacity and constant value. So they are represented as Cp and Cv. Fine. So we have to know that what is Cp. So it is actually, so now we are studying Cp. So it is heat capacity. We know that if for a 1 gram of substance, dq amount of heat is needed to raise the temperature to let's say uh, delta T. Okay, then heat capacity will be this one, right? Because per degree or per Kelvin we need actually. So at constant pressure, what will happen is that Q will be QP. QP is amount of heat at constant pressure. So we are right now just putting value delta QP by dt. Fine. Now we know that from the enthalpy part, I have previously told you that you should watch the previous video of mine of thermodynamics to understand these topics. So for recapitulation, actually I have incorporated this part also. So from enthalpy we know that H enthalpy is equals to U plus PV. U is here internal energy, right? So delta H will be delta U plus del PV, and if we arrange that one, we will be getting delta H equal to delta U plus VdP plus PdV at constant pressure, because here pressure is constant. So dP will be 0. So the rest part is dH equal to du plus PdV, and from the uh, from the uh, from the first law of thermodynamics, what we know is that first law of thermodynamics was du equal to dq plus dw, and we know dw is minus pdv, right? So dq will be du plus pdv, right? So du plus pdv is here also, so we can write dqp as pressure is constant here. So here we can put the value. So then Cp will be delta H by delta T, and we can write delta H equals to Cp dt. Okay. So delta H will be equal to Cp dt. This is an important formula. Same we will calculate for Cv. One important formula we will get after the derivation of the Cv also. So please remember it. And for the this is for 1 mole, and if n number of mole is given, that time delta H will be in Cp dt. Okay, please remember this formula. Now heat capacity at constant volume. Fine. Heat capacity, we know that delta Q by delta T for 1 gram of substance. At constant volume, again same, Q will be QV. Fine. CV will be delta QV by delta T. Now, how we get the value for that delta QV? Okay. Again, the first law of thermodynamics we know dQ equal to dQ plus dW, and minus PdV will be there. And at constant volume, what will be the case is that dV will be 0, right? So this term will be now gone. Now du will be dQV. So we can put the value of dQV here, and we get Cv equal to du by dt, right? And from here we get du equal to Cv dt. Fine. So these two formulas are very important. du equal to Cv dt and dH equal to Cp dt. Again, for n number of moles, it will be just n will be multiplied. Fine. Now coming to the ratio, this is very important portion. We will understand it again. We will see it again in the portion adiabatic case, adiabatic expansion when we did. So for the adiabatic process, actually this gamma heat capacity ratio is very important. So what is it actually? The ratio of heat capacity at constant pressure by and the heat capacity at constant volume. So we can express it like that way. So gamma will be equal to Cp by Cv. Please remember it. I'll make a video on the this actually. So equations of states and other important formulas for CPCB will be there. So we will read it again. Yes, equipartition theorem also I will be teaching. Okay. So in that part, I will again elaborately explain that how we can find the value for Cp and Cv and then gamma for various type of gases. Oh, I forgot to mention one thing here, that heat capacity can be expressed. I have told you that two ways, okay, but it is for only gases. For gas, we can mention, we can express the heat capacity by two ways. Okay, fine. Now the ratio we know, and one more important relation is there between Cp and Cv is Cp minus Cv equal to Nr for n number of molecule, and for generally we know that Cp Cv equal to R. So this is also important. Okay. So please remember these four formulas. Okay. 1, 2 and 3, 4 were there in the previous slide. Okay. Now the R is, what is R? Universal gas constant, and N is number of moles. Now equations of work or for work. Okay. So we will now take various kind of thermodynamic systems. Okay, and we will be calculating or derive how the equation of work uh, can be actually derived. Okay. So the derivation is not important here. We have to actually remember the formulas, because in the questions it will be mentioned like it is isothermal process or adiabatic process, something like that, and reversible, irreversible, all the things actually mentioned, I have mentioned in the basics of thermodynamics video. So right now only I will be taking various thermodynamic systems, and then the work will be, the equation of work for each case is very much important. Okay. So you have to have the idea of the all equations. So please be careful here. So work. First, in general, work is, we know, PdV, or PdV means dV is the change of volume, right? So we can write V2 minus V1, and P here is P external. Okay. Now we know P external is external pressure, V2 is the final volume, V1 is the initial volume. Okay. IPAC convention of work, I have previously told you that work done by the system is negative, work done on the system is positive. Now for expansion, V2 greater than V1, yes. Then W will be negative because here negative sign is there. V2 when greater, this term will be positive, and here it is negative, so overall it will be negative. Fine. So work done by the system, we can say. Because we know the convention, negative sign is there, so work done by the system. Now, for compression, we know V2 will be less than V1, right? So, if it is less than V1, that time this term will be negative. And here is one negative is present, so negative will be positive. So work will be positive, and work done on the system. I have explained to you with a common example or a simple example, like work done by the system. So you can remember it like that way, that I am giving money to the seller, okay, in shopkeeper, okay, and work done on the system is someone gives you money, your relatives can give you money, so you have now positive amount of money because money is adding in your account. Okay. So so your account will be full now, so positive, and negative is gone, the money is gone. Okay. So with that actually you can remember this one. So now equations of work which I have talked about. So first system is isothermal reversible expansion. Isothermal means, okay, in the next slide we will understand. Isothermal means, first, when we see anywhere the isothermal term, you should have this in your mind, that delta T will be 0. Temperature is not changing with time or for this process. Clear? Reversible means the change is very slow, right? Expansion means V1 to V2 is, if it is the volume change is there, then V2 will be greater than V1. Fine. And ideal gas we are taking for now. Okay, fine. Let's see. dW we know minus PdV. Okay. So we have to integrate it to find the actual W value, means work value. We actually want that, right? So now for ideal gas, we know Pv equal to nRT for ideal gas. So P will be equal to nRT by V. Fine. Put the value of P here, then nRT by V is there. Now the constant terms actually can go out of the integration, right? So constants are here, number of moles, obviously it is constant for a particular process. R is universal gas constant, and here as it is an isothermal process, C is constant, so it can go outside, and the rest of the terms are here which we want to integrate. So integration of 1 by x dx will be ln x, right? So here will be ln v, and the expansion is from, the system is expanding from V1 to V2. This is we should mention in the slide also. So V1 to V2 it is expanding, and it is the actually integrated form. So now we can put the value, right? So first we should put the value of V2, and then negative sign will be there. Then we will put the value of V1. So we can write from here that minus nRT ln V2 minus ln V1. This is there, and if we can arrange it in a proper way by the ln formulas, so we know that it will be equal to ln V2 by V1 only. Okay, so this is an important formula you should remember it. So this is for isothermal reversible expansion of gases. If it is not expansion, let's say compression, okay, then what will here the change will be only V2 will be greater than V1, less than, sorry, V2 will be less than V1. That time V2 is less than V1 means ln V2 by V1 will be negative. This term will be negative. So this term, this term will be negative, and here one negative is present, so work will be positive for the case of compression. But we have not mentioned for expansion, so obviously it will be opposite. But let's see. So for expansion, we know that V2 will be greater than V1, right? So ln V2 by V1 will be greater than 1 or positive. Not greater than 1, greater than 0, positive. So positive term is there, and here non-negative sign is there, so work will be negative. Okay, for isothermal reversible expansion of ideal gas. Fine, and we can rewrite this kind of equation like that way. If you see, just remove these all things. Okay, now we can clearly see the slides. So this, okay, so what I have done here, we know for ideal gas, okay, we know what we know. We know that V2, sorry, any what I am doing. So volume is inversely proportional to P, or P is inversely proportional to V. Anything you can say. So if we rearrange this with that actually idea, if we rearrange this equation, that will be, so this is inversely proportional, so it will be, so if we let's say it will be constant by P, so constant will be cut down, and P1 by P2 will be then there, right? If we put the value, K by P1 is here, and K by P2 is there, and K by P1. So P1 will be in the outside, right? So this will be also another form. When it will be applicable, when in the question it is not given the final and initial volume, but only final and initial temperature, sorry, not temperature, pressure is given. That time we can use this formula. Okay, and another formula is there. What is this? So ln is there, we can change it into log. So what will be there? 2.303 will be multiplied. That's it. So you should remember any of this formula, and then we can rearrange it to these two forms. Fine. Now coming to the real gas, isothermal reversible expansion of real gas. So we know these things, dW is equal to minus PdV, and integration will be there. And now for real gas, we know real gas, the equation is little different. Like real gas is van der Waals gas, right? So P plus N square by V square into V minus NB equal to nRT. This is the equation for real gas. And if we rearrange it, we can get the P is this one. So if we put the value of P here, this equation will be this. And if we integrate it, it will be like this. Okay. After putting the upper limit and lower limit. So this will be the equation for the case of real gas. Again, we can rearrange it. We can put the log by multiplying 2.303. We can do that. Okay. So now coming to the second system, second thermodynamic system, isothermal irreversible expansion of gas, ideal gas. Okay. So isothermal means, again, isothermal is there, so we will write delta T is 0, fine, T is not changing, and it is, sorry, it will be not reversible, it will be irreversible, fine. So we know for work it is minus P external into V2 by minus V1, and for irreversible case actually this is only applied, fine. V1 is initial volume, final volume, external pressure. We know these things. In vacuum, what is this? Vacuum means nothing is there. Okay. So P external, for this case vacuum actually there is no air. So pressure will be 0. So W will be 0. If we put 0, it will be 0, right? Now for ideal gas, PV equals to nRT, P will be nRT by V, and we can write like that. If we put the value of V2 and V1, we will get this one. So V will be nRT by P. Okay. So for the initial case, it will be nRT by P1, and for the final nRT by P2. So if we put that value, it will be this one. So now nRT can be moved towards this in front of the bracket, and if we multiply, if we solve this, this will we get. How? If you are confused, let's see this P2. Okay, yes. So it will be minus P2 is there, and okay, so I am taking nRT here outside, right? And minus sign is also there, and P2 into, there will be now P1 into P2, P1 minus P2. This will be the case. Simple. So now subtraction only. Now P2 will be cut down, and this will be the answer. So for real gas, we know this, and if we put the value of P again in this equation, we will get the value for real gas. We should not remember the values for real gas. We know for the real gas or van der Waals gas what is the equation of gas, and from there we can actually reform. We can actually get the equation for pressure, and we can put the value of pressure in the equation of work. Okay. So now important part. Isothermal reversible work of expansion is always greater than isothermal irreversible work. What does it mean? Isothermal reversible work of expansion is always greater than isothermal irreversible work. So reversible work, simply if we write reversible work is greater than W irreversible. How can we prove that? How? Think. Okay. So first, let's say a system is in, let's say a system is in one state. Okay. Let's say the pressure is P2 and the volume is V1, and now it is actually we are applying, or we are giving the conditions that first it will be it will okay, it will go through the isothermal reversible process, and then the isothermal irreversible. Okay, so we have to take the same system so that we can compare between the works. Okay, fine. We have to take the same system, right? So if let's say for example two ways of let's say two runways are there. So to compare between the two runways, we should actually take the same person so that he can run, and within the time frame he actually ending the contest, or with his experience or something like that. We can tell the differences. So their man should be constant there, and also the starting point. Okay, to compare between the two runways, how the actually paths are there, and how much time it takes for running, that kind of things. So for comparison, same person you should take. So like that way, we have to consider same system, and then we have to perform isothermal reversible, and then isothermal irreversible. Fine. Now, actually, we can prove it graphically. Let's say, okay, so let's say one system is in A state, and it is going to B state. One system. The system has the characteristics that its initial volume is V1. Here you can see V1, and initial pressure is P2. And in the B state, its pressure is P1 and volume is V2. So it goes from P2 V1 to P1 V2. Fine. So now we know for the reversible case, work is, for the reversible case, minus PdV, right? And for irreversible case, W dash will be minus P external into V2 by V1, V2 minus V1, right? So you must be thinking that same thing is there, right? P dV, dV means V2 minus V1. If you are thinking like that way, you are wrong. Why? Because in the PDV portion, we are taking every small steps or every small changes. But here only P external means here P external is the final pressure, means P1 minus P1 into V2 minus V1. But here, if we want to have the work value, we have to integrate it. dW will be minus P dV, right? So, below the curve, the area of the area under PV curve will be the work value for the reversible case. And for the irreversible case, you can see here minus P2 minus, let's forget about the minus sign here, only value is needed. So P1 into P2 minus V1. P1 means this is P1, right? P1, P external, and V2 minus P1. So what it will be? This is the actually the area for this portion, right? Where this is the P2 value, this and this, and this is the V2 minus P1. So this is V2 minus V1, right? And this is P2. So if we multiply these two, this is the area, right? So this will be the area for irreversible case. And for reversible case, area under the curve will be the work value, which is from here. Okay, if we draw like that, this whole area will be the work for the case of reversible. Okay, so how can we write here symbols? So this is the W reversible, and this we have taken, right? Like that way we have shown here irreversible. So in this graph only you can understand that only this value is W irreversible and the whole value is W reversible. So obviously what will be here? The answer. Obviously it is proved that W reversible is greater than W irreversible. Fine? We have proved it. Very important thing. Please remember it. Now again I have come to the equation of work. Now the case is adiabatic reversible expansion. Till now we have studied the isothermal. Now adiabatic case is there. So this will be a bit complicated than the isothermal case because here the equation of gas is different, which is PV to the power gamma equal to constant. Where gamma is again we have read it in the portion of heat capacity. So same gamma is here. You remember, right? Cp by Cv. Okay, so that's why I have taught you that one first. So Pv to the power gamma equal to constant, or we can write T v to the power gamma minus 1 is constant. This is the second form of equation, and this is the third form where T and V is there, and T to the power gamma and V to the power 1 minus gamma equal to constant. So here we can write that P1 V1 to the power gamma equal to P2 V2 to the power gamma. Same thing. P1 V1 to the power gamma minus 1 equal to P2 V2 to the power gamma minus 1. Okay. So like that way you can write here also. So this will be the equation of gas for the case of adiabatic reversible case. Fine. So now we know that here dq will be 0 obviously, and as dq is 0, this is from first law of thermodynamics, du is dw plus dq, dq is 0, so du will be equal to dw, right? And we know here that previously we have read it that du is equal to cv dt. Remember, right? Cv was du by dt, and we can write du equal to cv dt for 1 mole. Okay, and for n mole n cv dt. Fine, we can write that. Now cv is the specific heat capacity. Yes, you know by now. Okay, now the work will be from here. If we actually put the value of dt here, so we can after the reformation and derivation we can get the w will be equal to nr by gamma minus 1 t2 minus t1, right? So the derivation is not important here, only you have to remember the formula. Only one formula you have to remember, the other formula is also there. If we can rearrange that formula only. So this one also is the formula for work. You can remember both or only one. Fine. Now Cp is here a specific heat capacity at constant pressure. Why Cp has written? Because here gamma equal to Cp by Cv. So you should have the idea. So in the okay, so partition coefficient, actually in that part only I will be teaching you the equipartition theorem. Sorry, equipartition theorem part. I will teach you how to calculate the values of Cp and Cv and gamma. Okay. So for now, just see, and we will need it in to solve the questions from adiabatic portion. Now comparison between the reversible expansion of ideal gas in isothermal and adiabatic process. Okay, let's compare them. We have previously compared what? Isothermal reversible and irreversible, right? Now the comparison between reversible expansion of ideal gas in isothermal and adiabatic. So we are now comparing what? We are now comparing W iso and versus W ADIA. Fine. So we can compare it in the two ways actually. So again thinking, right? So thinking is the main important thing to solve any question. So first you have to think that how we can do that, right? So let's not see that part. Okay. Now the first condition is, it is actually the, have to discuss it. Just 1 minute. Okay. So now the thing is, if the final volume is same, first case. So if you see the graph, the first, you cannot answer it in a proper way. Okay. So if the final volume is same, first condition is this. Okay. So if final volume is same, so what should be the other values? First we have to take any system to compare it, right? So let's take a system which was in P1 pressure and V1 volume, which is, it is expansion, right? So which is expanding and forming. So the final volume is the same. Okay. So P will be different then. Okay, we have to take different. After that, if it is same, then it will be same. So for isothermal case, I am taking. So this is the process is. So again for comparison, we have to take the same person and we have to drive them towards different pathways. Okay, one by one. So first we are taking isothermal. So for isothermal case, P1 is the pressure, P1 is the volume, and Pi is the final pressure of the isothermal case, and the final volume is V2. Let's say. Okay, fine. Now for adiabatic, what will be there? For adiabatic, again the, so same system. So P1 V1 will be same obviously. So let's take a box here. Fine. So P1 will be same P1 and it is adiabatic. Adia. So after adiabatic expansion, the let's say the pressure is now PA and volume is V2 because here condition is the volume will be same. Next we will take the condition that when the pressure will be same. Okay, that also we will do in the later slide. So now if we look that for isothermal, the ideal gas will be will follow the PV equal to nRT formula, right? So we can write that P1 and V1 is equal to Pi and V2, right? So from here, if we write that Pi by P1, if we write, okay, just the ratio. Then this was multiplied with V2, so V2 will be there and V1 is there. Fine. This is for iso. So for adia if we take, then for adiabatic we know PV equal to nRT, that is not there, or constant, that is not there. Here what is the thing? P V to the power gamma equal to constant, right? So we can write like P1 V1 to the power gamma equals to, what was the final pressure of adiabatic? Pa and V to the power V2 to the power gamma. Fine. Now again if we take the ratio of P final by P initial equal to final has the P2 and P1 to the power gamma. Okay, so this is the equation number 1 and this is the equation number 2. So the gamma value, we know that gamma value is greater than 1, okay, for all the cases. So if it is greater than 1, then the this value will be greater. I mean to say, when we compare 1 and 2, okay, first not compare, first just write V1 V2 to the power gamma. It has to the power gamma term, is obviously will be greater than V1 by V2, and as it gamma is greater than 1. Okay, so now from here this we can write that if we just put the value of this here, so from 2 and 1, from 1 and 2, we can write that V1 by V2 to the power gamma means PA by P1 greater than the PI by P1. So P1 will be cut out and the P adiabatic will be greater than PI. Okay, these actually we got here. No. I'm extremely sorry. Here we should write like, sorry. This will be a little confusing. So that's why I have to reverse it actually. So, okay, now this will be fine. Okay, so we have to, like, V2 is greater than V1, right? So we have to rearrange it like V2 by V1 will be equals to P1 by Pi. Here also, uh, like that way, V2 by V1 to the power gamma will be equal to the V2, okay, P1 by Pa. And when we compare this one, this is not a one, this is the one equation and this is the two, then we can say that as V2 greater than V1 obviously and gamma greater than 1. So now we can write that V2 by V1 to the power gamma is obviously greater than V2 by V1, right? So then from 1 and 2, we can write that, what we can write? We can write that this was the value of P1 by PA, right? It will be greater than V2 by V1, only V2 by V1 here, right? P1 by Pi, fine. Now P1 V1 will be cut down and 1 by PA will be greater than 1 by Pi. Now from this we can write that Pi will be greater than Pa. So here the Pi isothermal, the final pressure of isothermal case is greater than the final pressure of adiabatic. So from this, how can we compare? Yes, we know that we now know that the pressure of isothermal is the constant, is greater than the adiabatic. Okay, but how can we apply this one for comparison? Now we have to plot the graph, right? So in the graph, so we know that Pi will be greater than Pa. So here, if we see, so P2, P3 is given, but this is the actually adiabatic graph. This is iso. This is iso. This is adia. Okay. So if this is the system, find the first starting point, and V2 is, let's see, the final volume is same. So when final volume is same for the isothermal and adiabatic process, the P isothermal will be greater than P adiabatic. So from the graph also you can see the P2 means the isothermal final pressure is here P2, and P3 is the adiabatic final pressure. Here is the process ends. So P3 is here, you can see from the graph P3 is greater than P2. Sorry, P2 is greater than P3. So same thing here. So graph will look like that. Fine. So we can solve that. Now the case 2 is if final pressure is same. We have taken that final volume is same, but here now the pressure is same. Okay, fine. We will draw it like same way. So if for, let's say, isothermal case, iso, okay. So first it was P1 and P1, fine, and the final pressure is same for both. Okay, now V is Pi final. V final is Pi for isothermal, and this is P2, let's say. Okay, for adiabatic case, what is the thing here? P1, V1 will be obviously same, and this is iso, this is adia, and the Va will be there, and P2 is same, obviously. Now we can again write as Pb equal to constant here, constant. So we can write P1 will be equal to P2 and Vi. Now again we can write like that, P1 by P2 will be equal to Vi by V1. So expansion, right? So Vi will be greater than V1. Here we are writing like that. So now here P1 V1 to the power gamma equal to P2 Va to the power gamma. Fine. So P1 by P2 will be equal to V1 by Va by V1 to the power gamma. Fine. Now we can compare it. The 1 and 2 can be compared. 1 and 2. Okay. So see, P1 and P2, P1 and P2 left hand sides are same. So we can write from 1 and 2 that Vi by V1 will be equal to the Va by V1 to the power gamma. Fine. So we can solve it by Vi by V1 will be equal to, if we take log, let's say. Okay. So log we have to take. Let's say we have taken log. Okay. So for if we take log here, gamma will be here, and log Va by V1. Now we have to compare that the final volume, final pressure we know the same, and we have to compare the final volume for these two systems. Fine. So here uh, Vi is greater than V1, we know, and Va is also greater than V1. So these two, log Vi by V1 will be positive. This will be positive value. This will be also positive value. And gamma is also positive, which means that this is also positive, which means that if we multiply these two, we will be getting this. That means after multiplication we are getting this, and all are positive. greater than one value. Okay, all has greater than one value. This is also greater than one. This is also greater than one. So, which we understand from here is that if we multiply these two values with positive values, we get this one. So we can compare these two and we can say that Vi by V1 will be greater than Va by V1. So Vi will be greater than Va. Let's just take it. Yes. Okay, I have checked it and this is the same because some mistakes can be there. So that's why I have checked this. And now we can draw the graph, right? So graph looks like this. How? So the system was at A state. Okay. So system is in A state here. System is in A state and system is in A state and this is B state. Okay. What is happening here? Okay, fine. So A and B. I'm sorry for this mess. So A and B, and A has, let's say, P1 and B1. Yes, we have read it, and B2 has uh, 2 for, this is for iso, and this slope is high. So for this reason, it is adiabatic. This is iso. So here this was P2 and Vi, right? And for this one, it was P2 and Va and P1 V1. Okay, fine. So here we can see from here that Vi is greater than V1. Obviously, this V3 is Va, right? And V2 is Vi. So V2 is greater than V3. So we can say Vi is greater than V1. Fine. So like that way we can compare these two values. And we know that what we know? We know that the area under the curve is the work. So here for the isothermal, see, the area is this much, and for the adiabatic case, the area is only. So comparing this, we can say here the W reversible, W iso, not reversible. W iso will be greater than W adia. Okay, let's go to the previous case. This one has also, this is iso. So iso means this one, and this is adia. Okay, so in this case also, this W iso will be greater than W adia. Okay, fine. Because we know that, please remember this one, that the work means for any graph, if we see any graph, that for any graph or anything, the reversible case, okay, for any reversible case, if graph is given, the work will be, and the obviously the graph is between the pressure and volume. So area under the curve for the pressure and volume graph is the work. Okay. So in both cases, we can see that W iso is greater than W ideal. Fine. Now coming to some questions. So 1 mole of ideal gas is undergoing the cyclic process ABCDA starting from a point A to 4 reversible steps as drawn in the figure. Total work done in the process. So if it is a what state function, that time if for the state function, if we are starting from A and we are again coming to A, that time for the whole process, for the cyclic process, the change was should be 0. But here work we want to calculate. Work is a path function, so it will depend on the path how the change is actually happening. Let's see. So 4 steps are there from A to B. First, if we look into, so A to B, what is the changing is you can see. So for this graphical problem, actually, you have to see stepwise manner the question can be solved, and you have to see that in this from A to B, what are constant and what are actually changing. The graph is between volume and temperature, and here if you see, it is a isothermal process, right? So for this process, T is constant, so T1, temperature is T1, fine, and delta V will be, or the V2 volume is changing like V2 minus V1. Okay, so we know work is for, okay, reversible case is given. So reversible, so work will be for AB minus NR T1 ln V2 by V1. Fine. For AB only, this will be the work. Okay. Then for the BC case. Okay. So here, let's say, okay, temperature is changing from T1 to T2. This is okay. So this is not a isothermal process, but one thing is there in this BC case. You can see that volume is not changing. Volume is V2. So it is a isochoric process, right? So for isochoric process, we know that dV equal to 0. Here is the case. But we know that work reversible is minus PdV. So as dV equal to 0 minus dW equal to 0. So work will be C for the case of DC. Next, we have another two, right? CD. So for the CD case, if you see that again the temperature is not changing, temperature is here T2 and volume is changing, but volume is decreasing. See the arrow is there. So from C to D the changing is happening and V2 is here greater than V1. But we are now right now just want to know about the work. So let's say this was W reversible. Okay. So let's say W dash reversible. It will be minus NR T2 ln final by initial. So final is here V1 and initial is V2. For CD case, initial was V2 and final is D point V1. Fine. So for the case of CD, this is the work formula. Okay, we got this one for AB, this is for BC and this is for CD. Now we have DA also. So for DA case, you can see that it is again an isochoric process. So dV equal to 0. So work will be 0. Fine. Okay. So 0 cases we have, I am removing from here so that I can get some space. Now we have to know the work done for the whole process. So process means here ABCDA, the movement, cyclic process. So for the ABCDA process, total work for any process actually, total work will be W1 plus W2 plus W3 dot dot dot. So all the works, sum of all the works from each step. Okay, that will be the overall work for a process. Here four steps are there. So it will be like W1 plus W2 plus W3 plus W4, and W1 is here is W reversible plus W2 is 0. This is W dash reversible plus 0. Okay. So we have to put the values of W reversible and W dash reversible. Okay. So here only I am writing equal to minus nr T1 ln V2 by V1 minus nr T2. Okay, I am removing here. Ln V1 by V2. So we have put the both these two values, so I can remove it now. Right? So now we can rearrange it, because in the options, if you see, this kind of answer is not given. So we have to rearrange it, like let's say if we take, so n is 1 here because no n value we can see here. So if we take the r outside, that time it will be the T1 ln V2 by V1 minus, here also minus is there, minus T2 ln V1 by V2. So we can write like here in the options V2 by V1 is there. So we can rearrange the V1 by V2 by plus, if we take T2 ln V2 by V1. I have taken negative as common, and negative negative will be positive. So here positive is there. So understood? So now R, and we can take now ln V2 by V1. Now it will be T2 minus T1. So it is a simple form of the total work. So answer will be this one. 4 will be the answer. Okay, this was from CSIR-NET December 2017. The next question is, it was also asked in I think GATE. Okay, so in this question, when an ideal monoatomic gas is expanded adiabatically from initial volume V0 to 3V0, its temperature changes from T0 to T. The ratio of T by T0 is. Okay, fine. Now, if we remember the case, uh, the equation of gas for the adiabatic case. Adiabatic case is given, and for ideal monoatomic gas. So PV to the power gamma equal to constant is there, and another form was T1 V1 to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1. This was another form, right? So now here V2 is 3V0, V1 is V0, right? And T2 is T, and T1 is T0. Fine. Now for the monoatomic gas is given, right? Monoatomic gas. So you should know the value of gamma. So I will make you understand in next video. But for now, please remember that it will be minus 5 by 3 R. Okay. So gamma is equal to 5 by 3 R. 5 by 3, sorry, not R. Gamma will be equal to 5 by 3. Fine. So if we take the, we want to know that ratio of T by T0, right? So if we take, so first we have to put the values here. Okay. So T1 is T0, right? V0 equal to V1 means V0, gamma minus 1 equal to T2 means T, and it is 3V0, right? So 3 also 3 into V0 to the power gamma minus 1. So gamma, putting the value of, after putting the value of gamma, so and also the I am taking T by T0 here. So T by T0 means here this one. So 3V0 to the power gamma minus 1 means 5 by 3 minus 1, and here T0 V0 to the power by 3 minus 1. So it will be V0 to the power 3 and 2, 2 to the power 2 by 3, and 3 also, sorry, yes, uh, hmm, yeah, 2 to the power 3, 2 to the power 3, and V0 to the power also 2 to the power 3. So it will be cut down, and answer will be 1 by 3 to the power 2 to the power 2 by 3. Okay. So gamma is 5 by 3 means 5 by 3 minus 1 is 2 by 3, right? 5 by 3 minus 1, 3, 2 by 3. Okay, fine. So answer will be B. So till now I will talk about for this class, and again we will meet in another session, and also I will make videos of thermodynamics, so which I promise to actually discuss. So that will be there, and how we can actually calculate the values for Cp, Cv, and this gamma, that will be also discussed. And so see you in the next video. So thank you for watching this video.